Hello everyone. Let us continue our discussion on the boundary value problem that we are trying to solve. So in the last lecture we saw that we have an issue when we are trying to find physically acceptable propagation constant. We ended up with negative beta that is not physical at all, right. So as I mentioned in the earlier lecture, the problem here is coming from the corners that we have. So we assume that the light is confined and this 4 corners are creating problems there, because the boundary condition in these 4 corners are very hard to define. So we just took it's all decay, right, and the 4 corners are going to decay, and we took that decay from the neighboring blocks, right. So that is the best that we could do, but that's not really accurate enough. So that is that is what led us to having this negative beta. So is there a way to out of this problem? Of course it is, right, and that's why we are going to discuss this particular approach here, which is called perturbation approach. So in perturbation approach, what we do is we are going to take the actual system and try to move to a comfortable definition and try to work from there. So what do we mean by that? So we take a solution chi, let us say, right, but then this is the exact solution, right, let us say chi, but then I said okay, let us approximate that solution to some chi naught. It is not exactly the same, but it is approximation. Similarly, we have a refractive index space that we take, n of x comma y is so far we have been using, but then how about taking an approximation of that space itself. So we are going to approximate that to some n naught x comma y, let us say. So that space may not be exactly the same refractive index contrast and refractive index distribution, but it is close enough, let us say. But how close it is? It is close enough for us to get a solution, and from that solution we will slowly migrate to an exact solution, right. So that is called the perturbation theory. It might look little confusing. What do we mean by that? It's like approximation. So it's like best guess scenario, right. So if you don't know where to start, right, you just put your finger somewhere and then say okay, I will start from here and then move in the direction that minimizes my error, right. It is basically a error minimization problem altogether. Okay. So let us look at how we can formulate this particular problem and how we can approach and solve this negative beta problem. At the end we want to solve this, but we will see whether we will be able to completely get rid of this or make it better. Okay. Let's look at that. So the approach that we are going to take, as I mentioned, is perturbation approach. Approach to correcting beta. So this is what we want to do. So we want to take this perturbation approach so that we can correct this beta. So let us start with our true mode, right. So what we call the true guided mode. So what is that mode? That is given by our function, right. So you could do it this way. Right. So this is our actual the wave equation, right. So that has the solution chi. So the chi is our actual mode here, right. So where your refractive index is n x comma y, right. so this n x comma y is what is causing the problem, right. So because of this high, the boundaries are very tightly defined. What if we reduce that boundary, right. So let's make it a little bit weak, or the distribution something that we could work with, right. So we take a modified refractive index, right, which is close to actual distribution. So we can start with that, okay. And the other, once we do that, right, then your wave equation should also be modified. So there you have the solution, instead of chi, the exact solution that we have, it is not going to be the exact solution that we have, it is going to be something else. So we need to take that into account. So it is not anymore the exact solution, but it is some other mode that you are going to get. So the rest of this is going to be so this is how it is going to be, right. So you have slightly perturbed or disturbed system, right. There will be infinite number of such solutions, right. So when you are going to change this, you can easily argue that, hey, this is not going to be the exact solution that you are looking for. Of course it is not, but then the probability of having such solution is really large. So then there are large number of solutions that you would get, okay. There is infinite number of solutions, that's a right way to say it, right. There are infinite solutions, but then there are only finite propagating solutions, there are finite modes that are guided. So here we could have possible to have infinite solutions, but finite propagating solution. So this is a very important understanding that we should have. There could be infinite solution, we should not be worried about the infinite solution, right. But what we are considering here is the subset of it, which is the propagating solution. Those propagating solutions are finite, right, but most of these waves are going to be unguided or radiating mode, right. So based on this completeness of the mode, in any reasonable distribution of electromagnetic field, right, that we have can be expressed by using superposition of the modes, which is something that we already saw in one of our earlier lectures, right. So we can write the exact form. So let me say chi here is the exact form of the mode that we have. We could have it as a combination of linear combination or superposition of all the modes or all the fields that you could have. Let us say we will start with something a trial solution, right. So this will be our trial solution for this particular mode, plus summation of n number of modes with their own amplitude and the field distribution. You have to watch out here on the indexing, right. So I used m for the trial solution, right, and n for the rest of the solutions or the other solutions, right, the other modes that are there, okay. So m here is not equal to n, right. So in the summation, right. So in this way the summation represents the total perturbation on the solution that we have, okay. So they need not be equal, right. So you take a trial solution your chi m, and then the rest of the things are other modes, and you can put it all together and to get close to what you want, okay. So you can make this summation infinite, and then make it go on forever, right, but we will have some sort of approximation, right, so that we do not go in circles, right. So, we could simplify this and then look at these modes, right, and not just these modes. You can also look at the orthogonality of these modes, right. So, orthogonality property could be used in order to take the subset of this finite number of modes, but yet they are going to be large in number. To make it manageable, we just try to make this handleable by using this propagating modes and orthogonality property, right. So, when we take this solution and then multiply, let me number this equation. So, if we multiply equation 2 with chi, right, and multiply equation 1 with chi n, let us say, right. So, we will end up with a system that has both exact solution and also the perturbed or the trial solution in this case. Okay. So, what we will do is multiply chi to equation with 2 and then chi n with 1, all right. So, if we do that, right, and then we can subtract these two. So, we multiply this and subtract. And then we need to integrate it over the surface. So, why are we doing this? To find the field in this particular region, right. So, that means you need to integrate these two equations that we have. One is exact solution, the other one is a perturbed solution. So, you want to put it together and then integrate it over this region, right, over the surface that we have here, right, along x and y. So, this is what is going to give us the correct solution. Okay. So, in that case, let us look at the exact solution beta square and then you have the perturbed one, integrate over the surface chi n over the surface that we have will be equal to k naught square. We can take it out because this has no implication on the integral here, x comma y minus n naught square d chi n ds minus, this is just basically multiplying 1 and 2 and then subtracting. I have not done anything special there, right. You can just do it yourself and check it out. All right. So, this is what you will end up with, right. So, multiplying it and subtracting the 2, you will end up with such a thing. So, you can quickly look at this. So, you will quickly notice that this will be gone. So, this will vanish, right, because of the second identity from Green's, right. So, Green's second identity, right, make this vanish, all right. So, now we have a much simpler expression for the exact beta between the perturbed beta k naught square, and it is going to be a pretty large integral here, n squared x comma y minus n naught square chi n ds for the surface chi n ds, all right. So, this is equation 4 and this is equation 5. So, this gives us an expression to determine the difference between the actual beta that you are looking at and the beta n, right. So, this is the simplified or the perturbed or changed waveguide cross section that you are looking at. So, there is a perturbation that you have applied, right. So, what is the difference between these two? Okay. So, this is what we are trying to optimize, right. So, you want to reduce this difference, and that will yield you the accurate solution here, right. So, in order to get the complete description, right, we must evaluate this this particular equation here, right. So, the equation number 3 here, and find how the distribution is, right. So, that means we need to integrate this in the surface or the x and y area that we have for this waveguide, right. So, along this waveguide, right. So, we need to look at how this particular distribution is going to be in this particular region, okay, between the exact solution and your perturbed or modified solution. Okay. So, there we are going to multiply that equation 3 with 1 and integrate over the waveguide surface. Okay. The same thing we did here, right. So, we had subtracted the 2, and probably I should add here and integrate over the area, right. So, this is what we are going to do again. So, that means chi n chi ds will be equal to the surface integral chi m chi n plus I will do n dash here, n not equal to m chi n to chi n dash. So, this is going to be interesting because it depends on the nature of these two modes, the orthogonal nature of these nodes, right. We can use the orthogonality using orthogonality. We could write this as delta m n dash plus a of n delta n n dash. All right. So, delta we all know, this is nothing but Kroneker's delta function. So, this delta is Kroneker delta function, right. So, this for some of you this might ring a bell that we have seen this when we discussed about orthogonality and orthonormality of the modes that we have, right. So, this will go to unity, this comma mn dash, right. This will tend to unity, right, only if m is equal to n dash. So, this is we all know this, then it will be orthonormal node, right. Otherwise, this is all going to be 0, right. Else so 0 elsewhere, right, or 0 instead of elsewhere I will say 0 otherwise. Okay. So, this is the condition for this, right. So, now whatever the integral equation that we had here, that equation 5, and we will make this as equation 6, right. So, now we can look at equation 5, right, and then look at this right, and we can do some modification, right, that will help us in. So, substituting from 6, right, from equation 6 here a n, right. So, that is what we had. Let me check substitution from 5. From 5, equation 6 becomes beta n square x comma y minus n naught square chi n ds. Okay. So, here m is not equal to m. So, that is something that you should keep in mind. All right. So, this is the linking equation, right. So, this will be calculated in terms of a n, right. So, that is to create a superposition, right, that resembles the actual mode, right. So, the actual mode is profile is chi. So, you need to recreate that particular mode, and that is how we do this. Okay. So, now it is generally sufficient, you know, to retain this 0th order solution, right, where your chi is very, you know, closely resembles one of the modes here, right. Let us say the chi m or chi m in this case, and also beta. So, beta resembles, or beta is very close to beta m, let us say. So, then we can replace chi and chi m and beta m here, right. So, when beta m is very close to beta, and again phi m, you know, very close to chi, then your a n will be written as k naught square beta m and we look at it, okay, beta m squared minus beta n squared over s n squared x comma y minus n naught square to chi s ds, and here again m is not equal to n. So, this is equation 7 and this is equation 8. And now the correction, so this is just on a n, right. So, correction for beta now. So, this is the final equation that we are going to write for the beta. So, that is basically beta square minus beta m squared. So, that is the difference that we have, or other case delta beta square can be written as k naught square integral n squared x comma y minus n naught squared chi m whole squared ds divided by. So, this is the general equation that can apply to any kind of waveguide. Okay. So, you can apply this to any waveguide, right, that will with which you should be able to find the actual propagating beta, right, by applying this approximation, right. The correction to the beta, right, is proportional to the index difference that you see here. So, that is very interesting to notice here, right. So, your correction that you are looking for is directly proportional to the index difference that you have here. Okay. So, when you have the index difference to be very small, that means you are very close to your the actual cross section or index, that you have physically, then your the difference in your beta will also be lower, right. So in the corner regions where the index difference from the assumed solution, right, it should also be noted that to get the true description of the mode field, right, so the radiation modes should also be considered here. Okay, so we should consider the radiation modes and the superposition of those radiation modes as well. So this is something that I briefly mentioned when talking about this particular relation, right. So when you take the trial solution and also add all these superposition of possible solutions, you could also add, you know, the radiation solutions as well here in order to firm up your progress towards the actual solution or the true solution, right. And the other thing to notice here is, you know, if you look at the final equation, the correction for P, it depends on the refractive index contrast that we have, okay, and also your field that you have, okay. So the overlap integral, you know, of the index, right, of the refractive index is not going to significantly affect your beta. This also depends on your field that you have, okay. So you can add your multiple modes here, right, that I was talking about, that are propagating through, right. The more the number of modes, the better it is, right. But when you are doing a finite set of modes, it is better to take the guided modes instead of just taking all the modes. So you can indeed add all the radiation modes that you want, right, to make the solution much finer, but then at the end of the day there is only limited resource you will have, you know, in processing this. So including the radiation modes is not going to significantly affect or influence your beta calculation. So it is good to just consider only the propagating modes, right, while, you know, considering everything is good, similar to Fourier expansion that you have, including all the coefficients will give you perfect reconstruction, but in a resource limited scenario, particularly in this case, it is not going to affect at all. So if it is not going to significantly affect your beta, why bother, right. So we don't have to take that into account. So now the question is, have we made our solution any better, okay. So that is something that we want to look at. So if you remember, initially we had this V number or V parameter with respect to B, we had a solution like this, okay. So we had negative solution, so what we call first order equation. So now we have made some progress, we have perturbation theory based approach, so that we just saw here, whether we will have a better solution. Unfortunately we can make it better, but not, you know, to the level that we want. So when it is outside the cutoff, you will have similar solution. When it comes close to the cutoff, it still does this. So this is coming from perturbation theory. So one can actually find this you know, numerically, but for the understanding sake, this qualitative approach is good enough. So what you see here is, still you won't be able to achieve, you know, positive beta when you are coming very close to the cutoff, okay. So this is again a problem, right. We have not solved this problem completely, entirely we have not solved. We have made it better, but not solved, okay. So that is going to be the topic of discussion for our next lecture, right. So with this we have made some progress, right. Instead of just blindly finding a beta, right. It is a blind find in the first order. Now we have some kind of approximation. We said we will not just find beta, but we will disturb the system, right. We will make some fine changes in our system. That means I am going to take all the possible fields that is available, right, and then put together a perturbed solution state, right, that I should be able to later on optimize the error and find out reasonably accurate beta. So, that was our approach, but it turns out even that approach you will not be able to get away with this negative beta. So, you still stuck with this beta when you are very close to your cutoff. Right. So, when you are far away from the cutoff, that means there are many modes traveling, it is all fine. When you are coming very close to the cutoff, so you have to really take a note of this, because when you are close to the cutoff, that means there are not many propagating modes there, right. So, if you remember the point that I mentioned, that include all the possible solutions when you are talking about superposition, right. So, you have exact solution, you have trial solution, along with the trial solution add all possible solutions that exist, right. That may include also radiating mode, right, to start with, but then later on we said we do not have to include all the radiating modes, because the integral is primarily driven by the index contrast. So, you are not going to get much from including the radiating modes. We can leave out the radiating modes and have only the propagating mode. But when you are coming very close to the cutoff, the number of propagating modes are going to reduce, right. So, when the number of propagating modes are getting reduced, your trial solution and your number of other solutions that you have, that other solutions is reducing now. So, when the other solutions are reducing from the trial, then getting to your exact solution is also creating a difficulty here, because similar to our Fourier reconstruction, the more the number of coefficients you have, the better the reconstruction. In this case, because you are close to the cutoff, you do not have that many solutions to help you out, right, or guided solution to help you out. So, that is the reason why even with this perturbed approach, you are still better, but not coming to a real solution to start with. Okay. So, how are we going to solve this, right? It looks like we are going in circles. We are making some progress, but then we are intrinsically limited by the approach itself, that there are not many solutions available, right. So, how are we going to solve this problem? We take an approach similar to the SLAP approach, right, which is called the effective index method, which we will see in the next lecture. Thank you very much for listening.